Let's do the homework question about Desmond's decrementer. This is Desmond's decrementer circuit, and it's made from a half adder with a NOT gate on one of the inputs and another NOT gate on one of the outputs. The question asks us, first of all, to give the truth table for a half adder, and then we can use that to figure out the truth table for Desmond's decrementer. What does a half adder do? It adds two binary numbers of place value 1, and it gives back the answer as a 2-bit binary number. And we can figure it out just by adding. That's to say 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is also 1, and 1 plus 1 is 2. And now we're ready to figure out what Desmond's decrementer does. It has two inputs, x and c in, which we can tabulate 0, 0, 0, 1, 1, 0, 1, 1, and then we can figure out what the outputs are. Okay, and how do we do it? Well, we look at what comes into the decrementer, then figure out what goes into the half adder. And then the truth table tells us what comes out of the half adder, and then we figure out what comes out of the decrementer. So if 0, 0 comes into the decrementer, then the x signal gets negated. So 1, 0 goes into the half adder. We're in this row of the truth table. Correspondingly, 0, 1 comes out of the half adder, and then the 1 gets negated to give us 0, 0. Meanwhile, if 0 and 1 go into the decrementer, then again the 0 gets negated, and we find ourselves in this row of the truth table. 1, 0 comes out of the half adder, and then the 0 gets negated to give us 1, 1. Now, in this case, when 1, 0 comes into the decrementer, that means we're sending 0, 0 into the half adder, 0, 0 comes out of the half adder, and then the 0 on the right is negated to give us a 1. And finally, if 1, 1 goes into the decrementer, then the 1 on the left gets negated, and we're in this row of the truth table. 0, 1 comes out of the half adder, and so the 1 gets negated, giving us 0, 0. So we've built the truth table for Desmond's decrementer. We were advised that we should regard Desmond's decrementer as a funny kind of adding machine where the inputs and outputs have slightly unusual place values. In particular, where x has place value 1, the carry in has place value minus 1, the carry out has place value minus 2, and the y output has place value 1. We're told that it might be good if we checked that Desmond's decrementer really is an adding circuit with these place values. So what we do is we add up the total place value of the inputs and compare it with the total place value of the outputs. So in this row, on the left, we have no 1s and no minus 1s coming in, so that gives us 0. And on the output, we have no minus 2s and no 1s, so that's also 0. In this row, in the input, we have no 1s and a minus 1. So our total place value is minus 1. On the outputs, we have a minus 2 and a plus 1. So our place value, total place value is 1 minus 2, which is equal to minus 1. In the third row, we have 1, 1 and no minus 1s. So our total place value is 1. And in the output, we have no minus 2s and 1, 1. So again, our total place value is 1. Finally, on the last row, we have 1, 1 and 1 minus 1. So our total place value is 1 minus 1, which is also known as 0. Meanwhile, on the output side, we have no -2s and no 1s, so the output is indeed 0. So yes, Desmond's decrementer is a circuit for adding when we have one positive input and one negative input. So we can use it to do a little bit of subtraction. For the next part of the question, we're asked to perform subtraction manually for this binary number, which has a 1 in the 4's column and a 1 in the 16's column, so it's 20. Any sensible person at this stage will predict that subtracting 1 from 20 ought to give us 19. So we have a check for the answer that we expect. Now, the instructions tell us to work from right to left with the carry here initially 1 and saying that the carry should remain 1 as long as the output needs to differ from the input. So what happens? Well, we try to subtract 1 from 0, but there's nothing to subtract. So effectively what we do is we add 2 to the top and to the bottom. We treat this 0 as 2 and we compensate by putting a 1 in the 2's column. We've added 2 to both sides of the subtraction. And now we can subtract 1 from 2 and give 1. Another way of looking at it is just that yes, the output has to be different from the input because we're subtracting 1, but we haven't actually found anything to subtract from, so we need to keep going in the next column. And the same thing happens again. We can't take 1 from 0, but we can take 1 from 2, and we can pay that back in the next column. 1 from 2 is 1. So now in this column we finally get a 1 that we can subtract from. 1 take away 1 is 0. And now we don't need to pay anything back in the next column. We've basically found something to subtract from and we're done. 0 from 0 is 0, and again nothing to pay back. 0 from 1 is 1, and we end up with a 0 in the last carry. So we have successfully completed the calculation, and look, we have a 1 in the 16's column and in the 2's and in the 1's. 16 plus 2 plus 1 is indeed 19. We have successfully subtracted 1 from 20. Now, let's have a look at what's going on. From these two numbers, the 0 and the 1, we computed these two numbers, the 1 in the output and the next one along in the carry. And look, when we have 0 and 1 as the inputs to Desmond's decrementer, 2 1s is what comes out. Moving along, if we have 2 1s coming in, 2 0s come out. And that's exactly what's going on in this row of the truth table for Desmond's decrementer. If we look here, we have 2 0s coming in and 2 0s going out, and that's exactly what goes on in this row of the truth table for Desmond's decrementer. And finally, in this column, we have 1 and 0 coming in, and 0 and 1 coming out, and that's what's going on in this row of the truth table for Desmond's decrementer. So what we can see is that Desmond's decrementer circuit is exactly the right component to do 1 column's worth of this subtraction of 1. So when we're asked in part C to construct a circuit that will subtract 1 from a 5-bit number, we've got a pretty big clue. we're told that we can use 5 DEC components and a carry-in signal of 0 or 1. Well, let's build a circuit which just follows our usual principle of building adding machines. We've got a 5-bit input with place values 1, 2, 4, 8, and 16. And we would like to subtract 1 from it. So how about sending in a constant 1 signal with place value -1. Now we have exactly the right place values to feed into Desmond's decrementer. We put in a decrementer here, and out come a 1 and a -2. So we've got the 1s for the answer. Now we have a 2 and a -2, so doubling up place values all round. Another one of Desmond's decrementers will give us a 2 and a -4. And now we have the 2s for the answer. Now we have a 4 and a -4, so going again, stick in one of Desmond's decrementers, and out come a 4 and a -8. And now we have the 4s for the answer. Moving along, another decrementer, we have it feed it an 8 and a -8, and out come an 8 and a -16. And finally, with our 5th decrementer, out come a 16 and a -32. We are then asked to check with the same example that our circuit does indeed compute 20 -1 correctly. So we feed in 1, 0, 1, 0, 0, and then we check that Desmond's decrementer sends the right outputs. If we feed in 0 and 1 to Desmond's decrementer, then out come 1 and 1 according to the truth table. That's 1 to the carry and 1 to the answer. Again, if we feed in 0 and 1, we'll get 1 out and 1 to the carry. Now if we feed in 1 and 1, the truth table tells us that we will get 0 to the answer and 0 to the carry. Feeding in 0 and 0, out come 0 and 0. Feeding in 1 and 0, out come 1 to the answer and 0 to the carry. So yes, when we start with 20, we end up with 19. Desmond's decrementer enables us to build a wide decrementer for numbers of any size.